So let's take some of the mystery out of these equations here, okay? The first thing is that you see these two equations for the period, and they must equal each other, right? I can write this formula this way, 2 pi over the square root of k over m. That's because of the way fractions work, right? I can divide by the reciprocal, right? Now, if you compare these two equations, you can see that omega is equal to the square root of k divided by m, okay? So that's kind of cool, right? We got a formula for omega, right? And then there's this equation for the acceleration that looks, it's magical. And you can get this, by the way, from the chain rule, but let's get it a different way, okay? Let's get it a different way. I'm going to erase that, right? So let's take a look at this. This is going to be then minus the square root of k over m, right? The quantity squared times x, right? Well, gee, if you square root this and then square it, right? It's just this k over m, right? So that just becomes minus k x over m, and it's like, well, where did that come from? Well, two formulas, right? Remember, Newton's second law is F equals ma. Hooke's law says F equals minus kx for a spring, right? If I push the spring to the right, there's a force to the left that's proportional to the amount I pushed it, right? So if I set these guys equal, minus kx equals ma, right? And I solve that for a, voila, I get this, right? Okay, so that's where this formula comes from, okay? Not that you needed to know that, but now you do, okay? A little bit of dynamics there. Now let's take a look at the energy formulas here, okay? As this oscillator is oscillating back and forth, let's say it's right here and it's moving like this, okay? It's got a position and it's got a velocity, right? So in general, its energy, its total energy, is going to be the potential energy plus the kinetic energy. Now, notice that we've got a total energy formula and we've got a potential energy formula, but we don't have a kinetic energy formula, right? Well, if you're paying attention here, right, if the total energy is potential plus kinetic, you can always make a formula for kinetic energy. That's going to be the total energy minus the potential energy, right? Okay. So I could make a formula here, couldn't I? EK. It's not in the data packet, but we can do it, right? If I go total minus potential, I get 1/2 m. Notice it's going to be 1/2 m omega squared x naught squared minus 1/2 m omega squared x squared, right? So let's factor out the omega squared. I'm going this minus this, right? And so we end up with x naught squared minus x squared. And you're like, that looks familiar. Doesn't it look a little bit like this? Kind of looks like that, right? In fact, if we take this formula and make a kinetic energy formula, remember kinetic energy is 1/2 mv squared. Sub that for v, right? Whoops, it goes there. Okay, that's going to be 1/2 m. And then instead of v, I'm going to put omega squared. And then the square root squared is just parentheses, right? X naught squared minus x squared. Okay, so this comes from energy, or it can come from kinematics, and it's a little bit of geometry, right? Okay, so there's a formula, right? But basically, you're not going to have that. So you need to understand that the total energy is potential plus kinetic, okay? And then one last thing, just for fun, just for kicks. Okay, let's erase this, right? Notice that this is our maximum velocity, isn't it? Isn't that our maximum velocity, right? So our total energy is going to be equal to our maximum kinetic energy, so 1/2 mv naught squared, right? But it's also going to be equal to our total potential energy, which that would be 1/2 k x naught squared. Remember, this was the formula for the energy stored in a spring, right? Okay, and the maximum energy is going to be that, right? And the reason it's the total energy is that when we have the maximum kinetic, right, we were right in the middle. We're right at equilibrium, so we have no potential. So the maximum kinetic is the total energy. And when we have the maximum potential energy, we're at the edge and our velocity is 0, and so we have no kinetic energy, right? Okay, so take a look at this formula here. Okay, this formula really isn't that just 1/2 m omega x naught, the quantity squared? Isn't that just 1/2 m v naught squared? Because v naught is omega x naught. Look at that. Woohoo! That's where that formula came from. Or maybe it comes from this, right? What is m omega squared? Well, m omega squared is equal to m times the square, remember omega is square root of k over m, right? Right? So m omega squared is just a ridiculous thing. It's really just k, right? M omega squared is k, right? So let's take this down here. We go 1/2 m omega squared x naught squared. Well, that's this thing, whoops. This is just k, right? So that's 1/2 k x naught squared, which is also the total energy, right? So there it is, right? Okay, blah, 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 blah. The main thing, though, right, is that you understand that the total energy is potential plus kinetic, right? Yeah. So let's do some problems here. Okay. A simple harmonic oscillator has an amplitude, that's going to be our x naught, right? Has a mass of that, has a period, that's our t, right? What's its angular velocity? That's going to be 2 pi over t, right? So that's going to be 2 pi over 0.86, and that is 7.306 radians per second. Okay, I could do the math here. Let's do it. Let's see, 2 times pi divided by 0.86. Yeah, there we go. All right, I've got it in my calculator now. Okay, what's the maximum kinetic energy? Well, the maximum kinetic energy, right, the EK, I'll call EK max, right, is going to be 1/2 m maximum velocity squared, right? Okay, we can do that, right? The maximum velocity squared is 1/2 m omega x naught squared, right? Where do we get that from? Look at that, right? This is the maximum velocity right there, omega x naught. Or you can get it from this too, right? If you put in 0 for this, right? If you're going through the equilibrium, it's omega x naught squared square root, right? Because that's 0. Right? Either way, it doesn't matter, right? Okay. And so, I guess I'm using the formula for the total energy. So these are the same thing. These are the same. Okay. So it's 1/2 1.12 times 2 pi over 0.86 squared times 0.48 squared, right? So let's do that. 0.5 times 1.12 times, the answer I just got, I'm lazy, I'm just going to square that, times 0.48 squared. And it's 6.887. Okay, so our EK max is the same as the total energy, is equal to 6.887 joules. Now, why is the maximum kinetic energy the same as the total energy? Because here's your equilibrium point. Our maximum kinetic energy is right when we're passing through this. Maybe I'm going to the left or going to the, let's draw a picture of me going to the left. Okay. Well, at that instant, my potential energy is 0, right? So I have only kinetic energy. So therefore, the maximum kinetic energy is the same as the total energy. Okay, because I have no potential. Okay. Woohoo! All right, let's look at the next guy. Okay, same situation, right? So this is our x naught. This is our mass, right? This is our period. We also know, by the way, that our total energy is 6.887 joules, right? So what's the kinetic energy when we're 0.23 meters from equilibrium? What's the potential energy there? Well, I don't have a formula for kinetic energy, but I do have one for potential energy, right? So potential energy is 1/2 m omega squared times x squared, right? Okay, which, by the way, that's just the same as 1/2 kx squared, because remember, this guy here is just k But we don't know the k. We just know all this stuff, right? So let's go with this, right? So 1/2 1.12 times 2 pi over 0.86. That's our omega, right? Squared, don't forget to square it, right? And then we're 0.23 from equilibrium, so our x is, that's our x, right? Our x is 0.23, and we're going to square that, right? So let's do that. So I'm going to go 0.5 times 1.12 times parentheses. Actually, you know what I'm going to do? I'm going to go up and grab that value for omega, square that guy times 0.23 squared. And I'm getting 1.581. Okay, so this is our potential energy, right? But it asked it first for the kinetic energy, right? Well, remember, the total energy is kinetic energy plus potential energy, right? There we go. Okay, so 6.887 is equal to the kinetic energy plus 1.581 joules, right? Okay, well, now I got to label that joules. Okay, so G, I guess I have to subtract, right? So our kinetic energy is equal to the total energy minus the potential energy, right? So that's going to be 6.887, right? Minus 1.581. And if I use the numbers on my calculator, I'm going to go grab that 6.887 number, subtract this guy. I get 5.305779 or whatever. So I'm going to say that my kinetic energy is 5.306 joules, right? Okay. So there we have it, right? Now, if you wanted to, by the way, we could find the kinetic energy by just saying, well, it's 1/2 mv squared, right? Right? If we sub in, right, because that's always kinetic energy, right? If we sub in that value for V, which is omega times the square root of x naught squared minus whatever, right? We end up with 1/2 m omega squared outside of the square root, or sorry, not square root. Okay, x naught squared, right? Minus x squared. And there's no square root here. No square root. You saw nothing. All right. And you could plug the numbers into that, right? This would be 0.48. This guy would be 0.23, right? This would be 7.306. This would be 1.12, right? And you'll end up with the same thing for the kinetic energy, okay? But these are the formulas you have, so let's use those. All right, let's do the last part of the example. Write possible equations for the position and the velocity, right? So I'm just going to go with this guy, right? X is x naught sine omega t, right? And we know omega is 2 pi over t. That's 7.306, right? And we know that that's our amplitude, x naught, right? Okay, so we can just write this way, 0.48 sine of 7.306 t. Woohoo! Make sure you're in radians when you do that. Okay, now, yeah, there we go. All right, I guess we have to say seconds to the -1, right? So this has no units, but let's not worry too much about that. Okay, now to find our velocity, right? Our velocity is omega x naught cos omega t, right? So we got to figure out what omega x naught is, right? So 7.306 times 0.48. Let's figure that out. Oh, the answer down here doesn't even do that, but we could do that. So 0.48 times omega. Let's see, where's omega? There it is. So 3.507. So if we wanted to write this equation, we could say 3.507, which is the same as 0.48 times that, right? Times cos of 7.306 t. There we go. And this will give us our equations for the position and the velocity, right? And if we wanted, by the way, if we wanted the equation for the acceleration, right, that's just minus omega squared times x, right? So we could go a is equal to the opposite of 7.306 squared times 0.48 times sine of, ta-da, woo, that's fun, isn't it? And this all comes from, and you can just stop watching right now, okay? This all comes from calculus, right? And you can just totally stop. You really should stop. You shouldn't watch anymore. Okay. So if our x is x naught sine omega t, right? Our velocity is just dx dt, right? Okay. So if we take the derivative of that, we take the chain rule, right? So omega, pull the derivative of the inside function out on the outside, right? So omega x naught, right? And then the derivative of sine is cosine, right? Ta-da! Right? And then if we take the derivative of this again, right? So acceleration is just the derivative of the velocity with respect to time, right? Which is the same as the second derivative of x, right? Okay, what's going to happen here is we're going to take another omega outside, right? So we're going to go omega squared x naught, right? And then the derivative of cosine is negative sine, right? Ta-da! And there's, we could make a formula. And you can just feel free to use calculus if you understand that, because these are just beautiful. This is why it's simple, and it's harmonic, and it's beautiful. Anyway, I'm going to stop talking here.